Welcome, everyone. My name is Jay Shah. I'm the Product Marketing Director for GE Digital Software's distribution portfolio and for the GridOS grid orchestration software. I will be one of the presenters and moderators for this GridOS Data Fabric webinar. Let me now introduce you to our other presenters. Andrew Gillis is the software CTO at GE Digital and leads the GridOS architecture and technology strategy. Zachary Gramana is the Director of Engineering for the GridOS Data Fabric architecture and technology strategy. After the webinar, we'll have a Q&A session, so please type out your questions in the chat window and we'll try to answer them during the Q&A. If we run out of time, we can address your questions offline or over email. To orchestrate the grid, including managing renewables at scale, keeping track of millions of distributed energy resources, and proactively managing disruptions from climate change, utilities need to unlock the power of data. Let's look at the need for a grid data fabric and the use cases it can enable. The energy transition and more severe weather events bring unprecedented complexity to the grid. Utilities need to ingest, keep track of, and model millions of distributed energy resources. They also need to operate across transmission, distribution, and the edge to manage multi-directional energy flows. Grid operators also need to address more frequent and severe weather events proactively versus reactively. To solve these challenges, utilities need to tap into the exponentially growing data streams from different parts of the grid and from outside the grid. Today, energy data is siloed between grid OT, IT, such as AMI, billing, and asset management data, and external, such as weather, wildlife, and traffic data. Even grid OT data is often siloed across planning, protection, transmission, and distribution. Utilities need to eliminate these data silos by securely connecting internal and external data sources to drive intelligent real-time grid operations. They also need to develop a data foundation for AI/ML to drive grid automation use cases, as robust training data is critical to leverage AI/ML effectively. That's where a grid data fabric comes into the picture. It is a necessary tool to remove data silos and bring together disparate data sources across the enterprise to provide a unified view and enable coordinated decision-making across transmission, distribution, and the edge. Let's now look at some of the use cases that a grid data fabric can enable. The first use case is a planning one. To enable planning use cases, utilities not only need to connect real-time grid OT data with environment data, they also need to be able to snapshot or archive this real-time and grid and environment data to build a solid data foundation that can show how the grid behaved in the past in relation to its environment. This operational and external data archive can serve as a source of training data for machine learning and AI to learn from. Additionally, this data foundation can also help with scenario analysis and grid simulations because of the knowledge of how the grid behaved in the past in relation to its environment now being available to grid operators. Use case 2 is a look-ahead one tied to distributed energy resources. For utilities that have situational awareness of DERs, they can use forecasting data and grid OT data to drive look-ahead analysis so that they can anticipate what will happen to the grid. For example, if it's going to be a very sunny day in the near future, a grid with high DER penetration may have the potential for backfeed violations or abnormally high voltage levels due to an excess of supply. The look-ahead analysis will allow grid operators to identify such future violations and drive future optimization decisions based on not just operational considerations, but also on DER program considerations to ensure feasibility of such decisions, as well as to minimize the total cost of operation. Based on this techno-economic optimization, utilities can send out DER dispatch decisions in advance, preventing potential future violations and taking full advantage of the flexibility inherent in the DER. As such, this look-ahead use case can only be realized by integrating DER asset data, forecasting data, grid OT data, economic and market data, DER program data, and settlement data. Use case 3 is about real-time integrated T&D operations. connection of disparate systems like energy management system or EMS, advanced distribution management system or ADMS, and distributed energy resource management system or DERMS together is critical for a system-wide view and coordinated operation across transmission, distribution, and the edge. This would enable advanced use cases such as outage response and restoration, emergency response such as load shedding and distributed black start, coordinated volt-var optimization, planned outage scheduling, operational situational awareness, and integrated switching, while helping manage multi-directional energy flows across DND. With a grid data fabric, utilities can enable a pragmatic and usable grid-specific digital twin depending upon utility maturity levels. This enables utilities to reduce complexity and implement a grid digital twin that's actually feasible. For utilities that are less mature, a geospatial model, a network model, and the data fabric can serve as a core grid digital twin. For more mature utilities who can tap into the physics model, applications data, external data, and asset data, they can enable a more advanced grid digital twin with state and environment data to enable simulations, scenario analysis, predictive maintenance, and failure analysis. For more advanced utilities who have analytics, AI, ML, and optimization capabilities, they can enable an intelligent grid digital twin capable of grid automation, and in some cases, enabling the grid to be self-describing and self-healing. Thus, development of a data foundation is critical for intelligent grid use cases. A grid data fabric is essential for AI ML powered applications, grid automation use cases, simulations, and scenario analysis. It is critical for the development of an advanced digital twin of the grid that can run operations in an automated manner while enabling the grid to be self-describing and self-healing. We cannot trivialize the problem of eliminating data and network silos or suggest that it's a utilities problem. We grid operators must solve it. GE Digital is in the process of developing a grid data fabric as a part of GridOS. Let me now hand it over to Andrew Gillis, our CTO, to show you the elements of the GridOS data fabric that exists today, along with a demonstration. Thank you.
Hi, everyone. I'm Andrew Gillis. What I want to do is show the data fabric in action. I'm going to be sharing my screen because some of the things I'll be showing is actually real demonstrations. So let me just do that. I'd like to share a little bit more detail about the architecture and some of the key capabilities behind the data fabric. I'd like to take a sort of some of the use cases that Jay talked about and dig into what's happening underneath. What's the technologies that drive this? And the data fabric sits within the wider GridOS architecture. It's divided into two components. You've got the platform and the applications. And the data fabric sits firmly within the platform. It's one of the key components of the GridOS platform. It allows us to combine data, to join data together, to facilitate some of those data-driven analytics and use cases that Jay referred to. So the data fabric at its core is really built on some core technology pieces and principles. Firstly, open standards and technologies. If you're going to share data and combine data, using open APIs and open standards is a key part of that sharing. And so the data fabric is completely constructed and built using industry open standards, industry de facto standards, and technologies. We talked about data being owned and operated by individuals, and really decentralizing ownership is key to the data fabric. By its name, the fabric brings together these decentralized traditional silos of data together. And so decentralized ownership of data has the advantage that the data is managed by the teams with the appropriate skill and knowledge, and by the technologies that actually best house that data. So decentralizing and taking the decentralized view is really what data fabric is about. There's an overhead to bringing data together. Although we allow the data to be decentralized, we centralize the metadata. So we have a central metadata system that combines all of the metadata from those decentralized silos. And metadata includes things like your schemas, your data availability, your data quality. All of this metadata is centralized. And what this does, it allows us then to access and easily find the decentralized data and treat it almost as if it were centralized. And it also allows us to do metadata-driven governance. This is where we can apply governance and who and how our data is used centrally, even though it is distally distributed. This also allows things like data lineage, understanding how the data is used and how that use changes over time, which applications, which services are using which data. And another key part of the data fabric is the self-service data access. This is really empowering users to be able to access data easily, to be able to turn and transform that data into actionable intelligence. And finally, there's a component of the fabric which really underlies flexible data integrations. When you're bringing data together, so you do need to move data, you need to collect data, you need to process it, transform it potentially, and export the data. And really, the data fabric contains all of these capabilities. The data fabric also within GridOS is focused on grid use cases. That's why we call it a grid data fabric. It's not a generic data fabric. It's a grid data fabric because it's optimized and tuned for grid data. We have a lot of very specific protocols, data types, data formats, SIM, and so forth. And it's really optimized for this grid environment that it's working in. So the grid data fabric is really the core piece that then allows us to orchestrate the data across the wider grid. So if you delve into the data fabric itself, there are some key pieces that provide these functions. So you have the organizer and the data orchestration tools, and these are just tools that allow us to organize and transform and process data around, and this allows us to do that data collection, this data export, and this ETL logic. We have the metadata catalog, and this is really what provides that centralization of metadata, allows us to apply our metadata-driven governance and so forth, this bringing together of all the metadata. We have the self-service capabilities, the ability to see and find and search the data, to transform that data into quick dashboards, to understand the data quickly. That's really self-service capabilities, and we have tools that enable that within the fabric. And we have the operational data store, which is, I guess, one of the key pieces that I'm going to demonstrate today. So I'm going to show you a little bit of the self-service and a little bit of the operational data store in action. So the operational data store itself is more than just a place to store operational data. It's one of the tools that we use to actually facilitate the easy transformation of data, the easy access data. And you'll see that in a demonstration, an example demonstration I'm going to give today. At its core, the operational data store is an in-memory, horizontally scalable database. So it's really a database that's designed in memory for fast, near transactional type interactions, yet really optimized for analytical processing. And it's horizontally scalable in the sense that if you want to grow your system, you've got new data types or new data quantities coming in, and you want to expand this, you just add new resources horizontally and continue to grow the system as your needs require. In a microservice architecture, which GridOS is, passing data around efficiently is also really important. And the operational data store for passing operational data around, again, provides these mechanisms to efficiently pass data around. It provides in-memory to in-memory data transport without actually that sort of data deserialization, serialization, or data transformation overhead that often can come with this. And this is based, again, on open standards and technologies, the same open technologies that are used in distributed machine learning, where you pass machine learning data around, we're using here. And one of the third capability of the data fabric that I want to talk about is data federation. And that's the bit I'm going to be demonstrating today. So data federation is really a type of data virtualization. You've got this data in your distal, distributed, decentralized data sources. And you want to treat that data as if it's one consistent, centralized, coherent data source. It's not. The data is decentralized and still maintained in the team by the teams and technologies of that distributed data. Yet the fabric and through the ODS or through the operational data store allows us to access this data as if it were one coherent data store. And I want to give this flesh this out with an example. So in this example, we have a relational database. We have the data stored in the operational data store itself, and we have some data that is coming in from a web site that happens to be in a GeoJSON file format. And we have these three different isolated locations of data. This file data, which is GeoJSON, the operational data store itself, which is an in-memory horizontal scale database, and a remote RDBMS. And we want to bring this data together. The use case I'm going to be giving is around fire data. So this is a screenshot of the National Interagency Fire Center for tracking fires, active wildfires in North America. And if you zoom into this website, those little dots actually turn into polygons, and you can see the fires are outlined, and there's metadata about those fires. And these are live, real-time fire information available through the APIs. And we can access this data through the APIs and pull back the GeoJSON files that say this is where the fires are, and this is their size, and the metadata and so forth associated with that. And we're going to combine this with operational data. This is data in this example that comes from our GridOS modular transmission apps. And these are running in GridOS and storing their operational data in that operational data store itself. And so we're going to bring together three types of data. One, that external data source, where are and what are the current active wildfires in North America. Two, operational data in our operational data store. And here we're showing the results of contingency analysis results from running on transmission lines, and this is the screenshot shows them in our self-service dashboard. And the third data source is the latitudes and longitudes of the transmission lines, which are essentially stored as just a long stream of latitudes and longitudes for the lines in a database. And we're going to bring these three data types together, and we're going to do that with a single SQL query. A single SQL query allows us to combine this data. And we will show in the example self-service dashboard how easy that is to then turn that into actionable intelligence, an enhanced risk dashboard in this example. And in this little insert box you see on the screen, you see one of the key components, again, very standard SQL, using a geospatial function, st-intersect. So here we're simply saying where lines intersect active wildfires. And we're doing it in a single SQL query, even though the data sources are very different technologies and in very different locations. So I'm going to do a demonstration right now where we're going to actually do a little bit of exploration of the SQL available data through the SQL Lab. SQL Lab, as you'll see in this demonstration, is simply a way of exploring the data quickly through SQL queries. So we call up the SQL Lab, and we're going to select Ampere database. Ampere is that operational data store. And remember I said it's the operational data store that provides that federation capability. So here we've pasted in some SQL, and I'm just going to look at a couple of key parts. So the first part is simply going into that database and pulling out our latitudes and longitudes. And it's transforming those latitudes and longitudes into SQL line objects. That then allows us to treat them in SQL as lines. And we can just run that selected query just to see that that's working. And see, here's all our transmission lines, and it's returning now a line geometry belonging to those. Here, this is what we're actually going to select in the SQL query. So we're selecting the line ID, but we're also going to bring some fire information. So the name of the fire code, what was the cause of the fire. This is metadata. And we're going to bring this data together only where there's an intersect between our line information and the fire information coming from those GeoJSON files that we've brought in from the NIFC. So this is really the simple sort of query bringing these three data sources together. And when we run this, we actually see there are two wildfires, but three lines that intersect those. So we have one wildfire called Forest Road and one called Whetstone, and the Whetstone one is actually affecting two lines right now. So because of that geospatial intersection. So you can see here that this dashboard allows us to quickly explore and find the data and play with the data and turn it quite quickly into some very informative intelligence. I now want to take it to the next step and add some of that operational data I mentioned, those contingency results, so that we bring together not only the lines at increased risk because of their proximity to wildfires, but we also bring together what are the current contingencies on those lines, then allowing potential operators to do further risk prevention or risk analysis, such as performing cascading contingencies. We're going to create this dashboard dynamically. So this is just the ability to dynamically pull together these data sets and charts that we've put together in the previous demo through the SQL lab. So really going to create a clean dashboard. We're going to call this dashboard Enhanced Risks Demo. And we're then going to drag into this dashboard some of those data sets that we created in the previous example. So one of those data sets is exactly that fire. It's a table showing what fires currently intersect with transmission lines right now. And we're going to drag that in a table form directly into the dashboard. So we have those, and in this case, we've still got those 3 results, which is there are those 2 wildfires, but 3 of our lines intersect them. We're going to do the same with contingencies. So we're going to search and have a data set. We do have a data set, which is our live contingencies. This is coming directly from the operational data store itself, that in-memory data set, and drag it also into this dashboard. And finally, we want to add a visualization so that we can actually see the lines and the wildfires overlapping, just to give us more confidence that this data is combining the way we want it to. And we can easily overlay the GeoJSON files, and we can even overlay those line information that we created in the previous SQL over a map view. And we do that here by inserting a simple mapping segment. So once we save this dashboard, we've quickly created an operational dashboard that gives you information about enhanced risks because of the location of lines with respect to wildfires. And we can play with this dashboard. We can go and have just confirm what was the SQL query that created those 3 lines that are intersecting those 2 wildfires. And we can do that simply by viewing the SQL query. You can see the query itself with that ST intersects right at the bottom of the query. We can also click now on one of those lines. So if we click on one of those lines, we can see that the rest of the dashboard adjusts, and we only now see contingencies related to that selected line. We can look at these contingencies and we can get more details about these, so we can dig into more information about that selected line and the contingencies associated with it. And this information then allows us to we can rank and highlight and pull out further what further actions we may need to perform because of the risk associated. And equally, we can look at the dashboard and zoom into our map view and actually see the wildfire then shown in red overlapping those 2 lines in this example. So this really shows you how quickly we want to be able to operationalize data. Within a very short amount of time, not only do we bring in some interesting and different data sources like active wildfires, we also combined it with operational data, giving the user and the operator a dashboard to empower them to make further decisions. What do they do about this enhanced risk? How do they then take this further and build further dashboards and further analysis? So really the data fabric in this example was playing 3 key roles. It was data federation, allowing us to have that really simple query, that simple SQL query that combined data in those disparate distributed data sources as if they were one single data source with that single SQL query. We also have the self-service capability, the idea that we can do this through a very easy data exploration dashboard and very quickly empower users with that information, leading them to better data-driven decision support. What do they do next? How do they deal with these enhanced risks in this example? And the third part, which I didn't really show here in great detail, is the data integration bit. Securely going and getting that information from those APIs and bringing that file, GeoJSON file information in and integrating it into the system was also happening behind the scenes. And these 3 things together were showing the data fabric in action, really empowering users with data. I want to hand this across to Zach now. He's going to do a little bit more depth and discussion about self-service and how the data fabric really can enable and empower users through self-service.
Hi, I'm Zach Romana, Director of Engineering for GridOS Data Fabric. As you can see, Data Fabric is bringing a lot of new grid data management tools for meeting the challenges of the energy transition. But for data to make its biggest impact, it also needs to be accessible to the folks at the front line of innovation, from the control room to everywhere else. So I want to take some time to talk to you about self-service and how it changes the relationship between information producers and information consumers. There's nothing surprising about this oversimplified definition of what a power system is, but it may surprise you to learn that to a data practitioner such as myself, an oversimplified definition of a data system is almost identical. And we even refer to the people whose job it is to run these systems using nearly identical acronyms. But the commonalities between the two really shouldn't be surprising, since they're each just one side of the same coin. Our transmission networks are managed with transmission software that deals with transmission data. The same is true for distribution networks, same is true for markets, and so on. In reality, there is a spectrum of people, and the lines are not always so clear-cut. On one end, though, traditionally, we tend to think of everybody in the control room or just outside the control room as being the power systems people, and the analysts and the engineers managing the underlying, databases and data infrastructure as being the data systems people. But the needs are not quite so clear-cut. The reality is people need different tools for different roles to accomplish different tasks in many cases. But ultimately, you need your tools to be fit for purpose because you need your data to be fit for purpose. But how do you determine what's fit for purpose? Well, there's a number of questions everybody needs to ask, whether you're a producer of data, trying to create a new data set or chart or dashboard, or a user of somebody else's data set or chart or dashboard. For instance, is there relevant data available for the problem I'm trying to solve? Does it represent what I think it represents? Just because I see circuit breaker identified in it as a part of the data set doesn't mean we're defining it in exactly the same way. For instance, is this a transmission data set or a distribution data set? Can I rely on it to make decisions? Is the quality high enough where it's an accurate enough representation of what's going on in reality? Or should I hold off on using that data because it's not reliable enough? And who's responsible for it? If I have questions about the data, if I want to propose a change to some aspect of that data or that chart or that dashboard, who do I talk to? And then most of all, how do I access it? It's fine for data to exist and for me to know and understand that it's reliable, who's responsible for it and what it means. But if I can't access it easily enough, then it doesn't necessarily bring the value that we all expect it to have. So the first step is finding data. But finding data in and of itself can be an overwhelming and challenging activity, especially for people who are historically not viewing themselves as data consumers or data practitioners. But in reality, a lot of us are experienced with working with data in some form or another, whether it's exporting CSV out of an application and then opening it in Excel or anything else. But we're used to doing it in very piecemeal, haphazard way, having to go from system to system to get the information we need. So we've provided tools to help making the activity of finding data much easier for everybody, regardless of whether you're just wanting to use some data or whether you're a data practitioner looking to produce a new chart or dashboard or analytic, either way. So we have a self-service mechanism that's easy to understand and work with for anybody. But for data practitioners like analysts, IT engineers, and even power users in the control room, let's say, we have additional, more in-depth ways of finding data, such as our metadata catalog, which provides a search engine for data and data products. We also need to understand the meaning and relevancy for the data. So within our self-service environment, we provide contextual clues to help you understand, for instance, what this column actually means. Because it's not always obvious from the description alone, And sometimes even if we think it's obvious and we understand what it's pointing to, the particular details that get played out in the data itself for, say, this particular column might have subtle variances in meaning, and providing a bigger description, a more in-depth description, helps you better decide whether indeed this is appropriate or not. In addition, for producers of data sets and producers for other elements in the system, such as charts and dashboards, we do provide additional ways for them to provide those contextual descriptions. Then accessing data is the next key challenge. And for that, we provide very straightforward, relatable tools that focus on the use of the information rather than focusing on the details of how that information is produced. So without needing to know technologies like SQL, for instance, a user can come in, and if you can do it in Excel, you can do it here. We provide ways to browse through existing data sets that you've identified that you want to use. You can see examples of what is in the data set and how it looks in a tabular form. And then you can choose different visualizations to represent that data, and tweak and configure how that data looks by adjusting scales, by adjusting colors, things like that. But for IT practitioners who are producing data assets, we also provide tools for them as well, such as through our SQL editor here, where they can author, explore data sets, author queries, run those queries to see data sets, and then turn those queries into new data sets that are usable through our self-service mechanisms, like the data discovery feature we just looked at, or charts, etc. We also need to understand if data is reliable. And so for that, we have simple contextual clues, such as a certification check mark or a warning icon, that allow users to very quickly, as they're discovering data, as they're looking through available data sets, to determine whether or not that data is deemed reliable or not. And for practitioners, we have much deeper tools that allow them to drill down and understand if a data set has a warning, why does it have a warning? What data quality checks are being done against that data set, so that they can understand exactly the shape of the data and whether or not the data is meeting expectations. So I hope that walk through self-service helps provide a little more context around how we see the relationship between users and data and information, but also collaboration within the organization in the new GridOS data fabric environment. Thanks.